So friends, now we are going to discuss a problem on depth first search. Okay, so depth first search is going to use the stack data structure which is having an implementation function of last in first out method. That is, we are going to remove the topmost element that is being present in the stack data structure. So this is the thing about depth first search. Now we can go for directly solving this problem. Right. So as I told already, we can start from any of the vertex if and only if they have mentioned the element from where we must have to start. In that case, we can use that as your starting element. So here in this case, I am going to start with W as my first element. Okay. So here what we are going to do is, for example, in breadth first search, we were finding all the elements that are adjacent to the selected vertex and we were adding it inside the queue, isn't it? But here it is just the opposite. We are going to select any one of the vertex which are adjacent to the vertex which I have selected, and only that we are adding it inside the stack data structure. So this is a stack data structure which I have added. Okay, so we are adding it and we are printing it. Okay, so that is the thing we are going to repeat until we have reached the last element. Then another technique here we are going to use is backtracking. Okay, so we are going to use backtracking in breadth first search. So this I am going to explain it to you while I am solving this problem. Okay friends, so shall we proceed? Right. So this is the given diagram. So there is a directed graph, sorry, it is an undirected graph. So I am going to take this W as my initial element. So what I am going to do, I am going to push it inside the stack and I am going to display it in my screen. So now W is being pushed and it is being displayed on the screen. So next, what you are going to do, you are going to find all the adjacent elements of W. So the adjacent elements of W are X, Y and Z. So let me take X. You can also select Y or you can also select Z. Here I am selecting X. So I am just adding it in stack data structure and I am printing it. Okay, I am just printing it. So next what I should have to do, I must have to see the next adjacent element of X. Okay, so X is being added in the stack, isn't it? So the next element of X which is adjacent to this is T and W. So if you watch, W is being already added. So T is not yet added. So now I am going to add it. Is there any other element? No, only T is the adjacent element. So I am going to directly add it. So add T and display T. Okay, you are going to push this T and you are going to display it, right? So that is the thing we are going to do alternatively. So now this is the topmost element now. So from T, okay, so is there any adjacent element? You just see R is your adjacent element and Z is your adjacent element. So T is having R and then Z. So these are all the two adjacent elements that are present for T vertex. So you can select any one. So I'm going to add R. Okay, I'm going to add R. Where I should add inside the stack, I should have to add and I must have to print it, isn't it? So add R. So R is added and I am just printing it. Okay, see, I am pushing and printing. Both are occurring simultaneously. Please have a note of it. Okay friends, so now what I should have to do, now the next element is, the topmost element is R. So from R you find what are all adjacent elements that are present. So from R if you see, Y is adjacent, Z is adjacent and T is adjacent. So R is having Y, okay, and Z and then T. So it is having three adjacent elements. In that, if you see what are all the elements which have been added. So T is added, isn't it? So Y and Z is not yet added. So you can select any of these. So you can select any of these, that is Y or Z. So now I am going to select Y. Okay, so I have selected this Y and you are going to add it inside the stack and I am printing it. I am adding it inside the stack and I am then printing it. Okay friends, so now this is your topmost element. Now from Y you find what are all the adjacent element that is being present. So from Y, what are all the elements that is being adjacent? So from Y, if you see, W is adjacent and R is adjacent. Is there any other element? Is there any other element? So no element, because W is already added and R is already being added, that is being visited. Okay, so in this point, we are going to stop the traversal, that is we cannot able to move anymore. Okay, so now if you watch and see, is there any element that is being left off from traversing? You just see W is visited, X is visited, T is visited, R is visited and Y is visited. Okay, still if you see, this Z is not yet visited. Okay, so for that what I should have to do? So for this case, I must have to implement a technique called as backtracking. So now what is a backtracking? So why we want to implement this backtracking is nothing but we are going to make a traversal implementations in such a way that we are giving a chance for this Z also to be getting visited. So that is called as a backtracking. That is, we are going to take a reverse direction based on this stack implementation. So reverse direction is nothing but reverse traversal for one step. Okay, we are going to make a reverse traversal by one step. Okay, so how we are going to find that one step? It is by using this topmost element. So for example, here the topmost element is Y, right? So this is the topmost element which is being visited. Okay, so from here, what is the next? How I can take the reverse direction? I can go here also, or I can go any other direction, but it's not here. So I can go like this, or I can go to R. So I cannot find in which direction to move, that is I cannot able to decide, isn't it? So what I am going to do is I will take the next previous element of Y. Okay, so the next previous element of Y is R. Okay, so the next previous element of Y is R. So what I will do is I will move like this, because I don't know, isn't it, whether I can move to W or I can move to R in order to reach this Z. So I cannot able to decide. So for that convenience, I will take the next previous element of Y. It is nothing but R. So I will move to this R location. Now at this instant of time, R is the topmost element. Okay, because I am standing here. So Y is being deleted from the stack data structure. So now R is the current position. See, once again I will tell you, Y was the topmost element, isn't it? So here only I have stopped my traversing. So I want to visit this Z also. What I should do? I must have to find the reverse direction, alternative direction for moving. So for that I am using this backtracking concept. So under this backtracking concept, I am going to move backward by one step based on the topmost element present. Okay, so here the topmost element is Y. Okay, so the previous element, that is the next topmost element, is R. So I will move from Y to R, not from Y to W, because this is your topmost element now. So remove Y. Now R is your top element. So now from R you find what all adjacent element present. So here from R, if you see, the adjacent element are Y and Z, isn't it? So the adjacent element are Y and Z. So if you see, Y is being visited, isn't it? So R is, Z is not yet visited. So now I am going to add this Z inside the stack data structure. So now I am printing this Z also. Okay friends, so like this only you are going to do this implementation of depth first search. Okay friends, then in order to check whether all the elements have been visited, okay, you can continue your backtracking technique. Okay, in order to check whether any of the elements have not yet visited, you can use this backtracking concept. So now if you see, visit is my topmost element. I have printed also. So this output is being completed. So now I am going to check whether is there any more element left out. Okay, so now visit is your topmost element. So the next element that is being present to visit is R. So from R, if you see, I have two adjacent elements, that is T and Y. So both are being visited. Okay, so both are visited. You can just leave. So now you take. So pop off this R also. Pop off this R. So now the next previous element is T. Okay, so the next previous element is T. So T has two adjacent elements, isn't it? Two adjacent elements are X and R. If you see, X and R is visited. Suppose if no element, if any of the element is not visited, means I must have to add it here. Okay friends, now that element will be your topmost element. So here, as all the elements are visited, you can pop this T. Okay, so now before T, this is the next previous element, isn't it? So now X is going to be the topmost element. So find the adjacent element of X. So it is W, T. So if you see once again, all the elements are being visited. So you delete this. So W is your next topmost element. So from W, if you see, X, Y, Z are the three adjacent elements. So all the elements are being visited, isn't it? X, Y and Z are visited. So you can pop off this W also. So finally, after checking whether all the elements have been visited or not, so this tag data structure will be empty at last. Okay friends, so this is the way you should have to do your depth first search questions. Okay, so I think so you will be having a clear idea of how to solve this question. Suppose if you have any doubt, once again you please watch this video from the beginning friends, right? So you will be having a clear idea of how to solve this. Okay friends, then now I am going to give you two questions related to that of BFS and DFS. You just try to solve that question. Okay, so we can discuss it in the next session. Bye and thank you.